Hello everybody. I decided to create a series of videos where I'm going to talk about numerical optimization. So basically how to make your code running faster. Now this topic is endless, in the sense we could discuss forever. There are so many tricks, so many details that can give an influence to the speed of the computation. But I will try overall to give you ideas, things to take care of, stuff to keep in mind. So I will give you many small examples and hints. So if you keep them in mind, then you can do some better coding. Now, if you are super expert about IT, or you have a very strong background in mathematics, especially the first videos will be maybe boring because you already know everything. But I want to make these videos useful for people that don't have a strict background in this kind of topics. So maybe people who study statistics or biology or, I don't know, finance, and they do coding, but it's not their main background. So I will start with very simple, basic stuff, and then I will raise the difficulty and I will go to more technical stuff in the hope that everybody will be able to keep up with me and to understand everything. At least I will try to do my best. So I would say I will teach 20% tips on IT side and 80% say mathematical tips. Mathematical in the sense some logics that you can use to create your algorithm and to ask your computer to do computation. So if you do some mathematical simplification on the mathematics, then the calculations are simpler and then faster. In this first video, I will basically do this, just some basic stuff, mathematics related to computers. And in the next video, we will raise levels. So let's start with an immediate example of what I'm trying to teach you. So let's say I ask you to compute these products you see in the screen, where I take a large number, say 1, 2, 3, 4, 5, 6, 7, 8, 9, and I ask you to multiply by 13, or more complex by 349. I'm pretty sure if I ask you to do so, it will be a bit challenging. You need maybe paper and pen and a bit of work. It's not simple, because the algorithm of the multiplication is not simple. Now, if I ask you instead to multiply this 1 to 3 number by 10 or by 1000, I'm pretty sure you can do very easily and very quickly, because you don't really make the multiplication. You just take the zeros and put at the end of the number. You see here highlighted in red the numbers. So something like this can be done also when you do computation, when you write a code. And why? Well, basically, the computer uses the base 2. Now we count, humans count up to 10 digits, computer counts up to 2. So when you multiply by 2 or you divide by 2, you can use somehow the same tricks. So let's take an example. I ask you to multiply 21 by 2. It's 42. But if I ask you to multiply 574 by 4, already can be a bit challenging for a human. But when you go in base 2, here I reported the numbers, they are, so 21 is 10101. When you multiply by 2, you just multiply by 10, and you can apply the same trick. Put a 0 at the end. And when I ask you to multiply by 100, so the second number, I hope you can see my mouse somewhere here, then you see you add the 2 zeros. So you can do the same when you do. You can apply the same trick when you do coding. And in order to understand this, I will use Python, okay? I will use Python because most of the people do coding in Python, but you can try in any other language. So the trick I'm telling you will apply more or less to every coding language you can use. And actually I suggest you to try in different languages, not just watch my video, but do some exercise on your side. So let's go to Python. Here we are. So, if you are not familiar, the first two lines are just importing some libraries that we will use later on. And in particular, we use NumPy, that is a library you use to do some mathematical computation. I just rename it like NP for simplicity, but it's not mandatory, just useful. And time. Time, we will use this library to basically measure the speed of our code and the execution time. Now, as I said before, you can try to multiply 21 by 2, or you can use the same trick. What are we doing here? We are telling to the computer, shift the bits. So, by one position, for example, when we multiply by 1. Or if I take and I want to multiply by 4, we shift the bits by 2. Now, let's go back to the presentation I was giving you. If you observe the first line here, when you add a 0 at the end, you are shifting all the bits by one position. And when you multiply by 4, so 1, 0, 0, you shift the bits by two positions. So, going back to the Python, we are actually trying to do the same, and we can verify whether what I'm telling you is true. So you just run the code and you see that multiply by 2 or shift by one position, you get the same result. Multiply by 4 or shift by two positions, you get the same result. Now, why I'm telling you this? Maybe asking a computer to shift bits is faster. It's exactly as it is for us as humans. When you multiply by 100, you add 2 zeros at the end. You don't really make the multiplication. So in order to do this, I will use a trick that I'm gonna teach you to measure the time, the speed of the execution time of this instruction. That's basically you set up a variable that's taking the time when you start the execution, and you save this time in a variable. Let's call it start. And then at the end, when you finish the computation, you measure the time at the end, and you just print the difference. So you get the difference in time, so the amount it takes. And actually, since this execution is super fast, I add also a loop, right? And I loop basically over this amount of time. That's 100 million times. So computer, you are really fast. I cannot see your speed. Let's repeat the same instruction 1 million times, 100 million times, and so we can magnify the time and have a reasonable assessment of the speed. Now I will do first the basic execution of this bit shift. I'm not doing any other stuff. I'm not assigning, I'm not printing. I just want to measure the naked time we need to make this speed. I'm trying to teach you this. That's somehow a simple trick that you might be already aware of, but later on we will use this many times, so I want to make it real clear to you. And then what do? We do exactly the same by the multiplication. So basically we start measuring the time, we do 100 million times the bit shift, and we print the total time we used for this, and then we do the same by multiplying by 4. Let's try to run this. Right, and now while it's running, let me just put a comment. First of all, the execution time might be dependent on the environment you are using. So now on my machine, I get that both operations, they use the same amount of time, so they go at the same speed. But if you try on your machine, you might get different results. Why you can get different results? Basically, the execution time depends on the environment you are working with. So, are you working with Windows? Which version of Windows? Are you working with Linux? Are you working with Apple? But then, are you using Spider? Because I'm running Python inside the IDE that's Spider, but you might be using another IDE. So, and then you might use a different compiler. So even the same Python, when you use a different compiler, might run at different speeds. Actually, some compilers knows this trick that I'm teaching you, and they are so smart that they will use the fastest between the multiply by 2 or the bit shift. But if you use a different operating system, IDE, language, compiler, and so on, maybe you will get different results. So worth to try, worth to be aware of this trick. maybe you will never use in your life this trick, but if you have in mind it, this can be maybe useful later on at some point when you do some completely different task. Anyway, let's go back and observing the results. And you can see for this instruction we get the same result. You should try with your own language, coding language, and verify whether it's the same. In principle, the bit shift should be faster. I guess here the compiler is so smart that it recognizes that I'm multiplying by 4, so just doing the bit shift. If here I put dot, now I'm forcing this 4 to be not an integer number, but something else, and we can try as well to execute the instruction. Since here is not an integer, maybe the compiler will use a different algorithm and will run at a different speed. So let's wait a few seconds and observe the result. Actually, it's going a bit faster, but here we can take this occasion to observe another point. Before I ran the code and got 5.6 seconds, now I got 6 seconds to run exactly the same instruction. Why do we observe this difference? Well, when you run a code, Spider will go to the operating system, in my case Windows, and say, sorry Windows, can I use the CPU to make my calculation? And Windows will say, oh yes, but wait, I'm finishing, I don't know, I'm running antivirus, I'm downloading some data, I'm recording a video. So wait in a queue, and then it will use the system. And then while the process is running, still maybe the antivirus is coming and say, oh, I have priority, pause, give me the CPU, and then come back. In principle, this function should take the clean somehow amount of time, so should remove this queuing time, but this works only partially, so that's why sometimes you get 5.6, another time you get 6 seconds. You should take in account that there are some fluctuation as well. What I'm telling you should let you understand a bit more how the computer works and how the test should be taken, with the, bit stop and thinking what you're doing, and don't trust too much the number you get, run a few times and see what the results are. I'm trying to teach you a methodology rather than a specific trick. Now let's go to another example. Let's consider the case you want to use a matrix like this one. Let me run this part of code. So actually I fill the matrix with elements where the number remembers somehow the position of the elements itself. So the element that is in the first row and first column is 1, 1. First row, second column is 1, 2, or 12 if you like, and so on and so forth. Second line, first element is 21, and so on. Now if I print the value of this variable, you will see that in the memory is stored in this way. As human, I look at this like a matrix, but Python decided to store in the memory this as a list. Actually, I put it here as well. Now, why is it important to know what the computer is doing? Let's say you need to make many calculations on this matrix, and you need to be fast in getting to the element you need. For example, you have to run a loop where you go through all the elements. Now, to run through all the elements, you need 2 for loops, or whatever. If you use another language, I don't know, can be do or while, anything. Basically, the first loop will run through the lines, the rows, and the second through the columns, and we can just print the elements. If I run in this way, just print, and you see, we go 1, 1, 1, 2, 1, 3, 1, 4, and then 2, 1, 2, 2, right? So basically, I'm accessing the data in this matrix exactly in the same way as they are stored in the memory. Now, I might run the code in a different way. Let me run it. What I'm doing, I'm running columns in the external loop and rows in the internal loop. So basically, I'm saying, okay, take the first column, and then you go first line, second line, second line. So I'm taking this element, then this element, and then this element. And then I go to the second column, this element, and so on and so forth. Now, if you see, while I'm clicking on this, look at the second line, which element get automatically highlighted. You will see that I'm taking this element here. Then I go here, I'm jumping in the middle of the this array, and then I go third element, I go almost at the end, and then I go here and I jump in the beginning. So exactly as I'm highlighting with the mouse, this will do exactly the same in the memory when you access to the data. So the second loop will not access the data in a sequence, nice sequence like in the first case where I was just accessing first, second, third, and fourth. Now the computer will spend time to jump from one point to the other in the memory. It's important to be aware how the data are stored in your memory to improve the speed. Actually, if I remember correctly, in past, in Fortran, it was better to access in the second way, while, for example, in C was better to access in the first way because they were storing the data in a different way in their memory. Now, if you run whatever coding language with whatever compiler, you should better try to understand how they access the memory, especially if you are doing a lot of, for example, multiplication between matrices or so on. Let's say we can do the same trick as before. Now we define a very large matrix of 20,000 elements, right? I fill it with just random numbers, where NumPy, the nice mathematical library I told you before, is providing us the random numbers. And then we can measure how much time it takes to just access the data. By this instruction, I'm just getting access to the data. I'm not really doing any other operation. And as well, we can measure the time it takes to. So let's start running this and compare, right, how much time it takes going row first. So first row, and then you go all the elements by column, second row, and all the elements by column. Or do it the way around, first column and then each element, second column and then each element. Now, this matrix is very large. If you think of 20,000 times 20,000, we are speaking about 400 million elements. So this process will be quite heavy and will take a bit of time. So during this video, I will just speed it in. So here we are after almost 10 minutes, the computation finished. Well, maybe I could ask for a smaller size and run it faster. But anyway, the point is, look at the result. When we access the matrix by row by column, so the first loop here, it takes 250 seconds roughly. When you go column by row, it takes roughly 300 seconds. 300 seconds will be, I don't know, 20-25% time slower, let's say. The first case is a bit faster. Now, if you try on your machine, you for sure you will get different results. If you try with different languages, compilers, IDE, everything, you will get different results. The point is not actually to make the matrix faster itself. The point is you should understand that the computers are machine and they do stuff. And if you understand what the machine is doing, you can do better coding. Think if you are trying to make parallel computing or, I don't know, accessing server, downloading data and so on, handshake, this and that. If you understand, you can do better. If you don't understand, if you are not sure, there are basically 3 strategies you can adopt. The first strategy is to ask some friend, some colleague that is more experienced than you. The second strategy is go on Google. There are people discussing about any topic. For sure you will find some hint. Or you can ask a question to some specialized forum. And the third strategy you can try is just what I did here. Put down the code, run it, measure the time, try, play around, if I fix this, if I fix that, let's see. And you will for sure understand better and will improve the execution time of the code. So through this video I was trying to give you an idea, the way of thinking. There are million tricks. I cannot teach you everything. Actually, I'm not the most expert about this topic. I'm not the top expert, but anyway, I gave you an idea. Try to keep it in mind to improve. In the next videos, I will focus much more on the mathematical side. So what I mean is basically to think better algorithms, keeping in mind the mathematics. So if you think, you simplify the calculations already at the algebraic level or whatever, a priori, then you can create a faster algorithm. On this, I feel much more confident on this topic, so I hope you will be interested in. For now, thanks.